Good afternoon, everyone. In Tom's case, it's good morning, but for in India, it's good afternoon. And welcome back, everyone, after the lunch break. So now we are going to have these two talks by Professor Tom Beucler. So a brief introduction about Tom Beucler. So Tom is an assistant professor of environmental data science at the University of Lausanne, Switzerland. I hope I pronounced it correctly. Is it? Lausanne?
Lausanne? Yeah, that's great.
Okay. So Tom leads the data-driven atmospheric and water dynamics laboratory, the first research group worldwide dedicated to bridging atmospheric physics and AI. Tom holds a PhD in atmospheric science from MIT, where he studied tropical convection. His postdoctoral work at Columbia University and UC Irvine focused on deep learning for climate modeling. So that's about Tom, and I think we are good to go then. Tom, over to you.
Yeah, thank you so much for this introduction. Thank you for inviting me. I know it's sometimes challenging in such hybrid settings to ask questions, but I'll be keeping an eye on the Zoom chat. And is there a way for people in the room to ask questions? I don't know if I can hear you people in the room.
Yes, so I like if anyone has questions, like they will pass around a mic and they can ask in between also.
Okay, fantastic. And I also want to thank all my collaborators. This is very collaborative work. With such interdisciplinary projects, it's almost impossible to conduct the work yourself. So I'm listing some of them here, but you can peruse. I listed a couple of papers, the co-author list and the acknowledgement list. It's certainly collaborative work. To just give a bit of background about me and my group, so as was kindly said during the introduction, we are, I think, the first group where we, from the get-go, decided to investigate and bridge atmospheric physics and artificial intelligence. We work on various topics, so we think about what Earth system modelings of the future would look like, next generation Earth system modeling. I'll talk a little more about it later on. We work a lot on extreme weather events, whether it's for data-driven forecasting, post-processing, or downscaling. And finally, I hold the chair in environmental data science, so we help scientists from all fields of earth and environmental science to build reliable models from the data they collect on the field or they get using running high-fidelity models. But what I want to focus on today is really the two-way interplay between physical knowledge and machine learning. So on the one hand, physical knowledge, and I'll tell you more about it in just a minute, can be used to improve, guide the data-driven models we build. And on the other hand, and I'll talk about it if we have time, but I really want to focus on the first part mostly because it seemed a bit more aligned with your summer school's objectives. You can use machine learning with high fidelity data to discover new knowledge. I really think we've reached the stage where we can go past a proof of concept or confirming what we already know and really make new hypotheses about climate, atmospheric processes we are interested in. And just to put everyone on the same page, I'm sure you've heard a lot about machine learning already, but I just want to add that I will be using the term quite loosely. So in my talk, machine learning will include all algorithms that learn a task from data without being explicitly programmed for that task. And in a supervised context, we will be targeting samples with label that we'll call Y. For example, in the atmosphere, this can come from processes for which we have data, good data. It can be high fidelity model data. It can be observational data, but not necessarily a simple or straightforward theory from it. And so what machine learning can help us do in the supervised learning is bridge variables we have more knowledge or control on. So that would be, for example, vertical profiles that are relatively coarse resolution of temperature, of water vapor, to processes such as convection, extreme storms, things we understand less, but we've observed in the past. And so a machine learning algorithm can learn what we call a mathematical mapping from a vector x to a vector y, and it can do so by minimizing what we call a loss function. In a standard supervised setup, that loss function is typically an error between what the model predicts, y, and the true labels, what the model predict y hat and the true labels y. And we use variants of different optimizers. What really helped fuel the machine learning revolution in our field that I would argue, you can argue started roughly 10 years ago, is progress in optimization and compute that allowed us to use variants of stochastic gradient descent that work very well for big data. And so unlike older algorithms, because we've been doing optimization for a long time, these algorithms work best in the limit where you collect a lot of data. And as we collect more and more data, that's why these algorithms are more and more successful, because they can describe the environmental complexity around us. So you may ask us, okay, if this works very well, why do we even care about physical knowledge? And this will be the theme of the first part of the talk that we'll be spending the most time on. And from a research perspective, I want to show you that using knowledge, exact knowledge, or even sometimes approximate knowledge, to guide the behavior of data-driven algorithms may improve their consistency, physical consistency, the generalizability across regimes, and may reduce error in some cases. I'm putting a star because I don't want to have an overly simplistic presentation. There's always trade-offs in these cases, and I'll really dig into why. They also, of course, such knowledge can also improve interpretability, transferability, data efficiency. And so I'll show you concrete examples where that is the case. And the first example that I like to start with is a simple example from the forecasting world where we physically constrained post-processing using exact knowledge of atmospheric laws. But before I do that, since this is a summer school and I got a prompt that it was best to give short tutorials, I want to give a short tutorial on physics-guided machine learning. And then I'll take questions. And also during the question session, if I'm speaking too slowly or if this is too easy or too hard, just let me know and I can adjust it for the second part of the talk. So why do we even care about physics-guided machine learning? There's a good amount of evidence that in many fields, purely knowledge-driven models may fail, or they may be very limited. One field where there's been a lot of debate and interesting and controversial literature about this is hydrology. And so this is a paper from Gray Nearing, who's very good at writing controversial papers, which means they are fun to read. And so this is a very controversial title. Why do we even care about hydrological science now that we have machine learning and data? And what he argues is that if you look at streamflow models, so these are models that are going to predict the time series of streamflow based on, for example, precipitation and some of the catchment properties across the US, and you compare prediction made from a state-of-the-art calibrated conceptual models. So these are these interesting semi-empirical models that hydrologists often use. I'm not a hydrologist myself, so for full transparency, if you ask me too many hard questions about such models, I may not be able to respond. But my understanding is there a mix of physical understanding and some statistical laws and properties about the catchments. And they're used and they calibrated on a per site basis usually. But some of these models are general enough to be calibrated across sites. And so what you can do is you can compare how the prediction of these models, how well they do using a performance metric called the Nash-Cliff efficiency, which is really close to the coefficient of determination. It's a coefficient of determination for the streamflow that hydrologists use a lot. To the machine learning model. In that case, it's a long short-term memory. Maybe you've already learned about it this week. It's a model that's specialized in processing sequences, and as such, it's very appropriate to process time series. And what you can see is that the machine learning models perform well for most stations. So it's much easier to calibrate. It generalizes better across, and in this case, it's generalizability across catchments, so spatial generalizability. And so Greniering uses this to argue that, okay, maybe machine learning models have a tiny bit to learn from the semi-empirical model up here, but mostly they much more versatile, and they do better if you calibrate them across catchments. And there's a really provocative prompt here, which is why these papers are often to read, but you have to be careful in such debates. That's kind of flipping it. You know how domain scientists can often come and can be skeptical of machine learning advances. And here it's written, it is up to hydrologists to clearly show where and when hydrological theory adds value to simulation or forecasting. And as a physicist, I think it's a fun challenge, right? To flip the script a little bit and ask yourself, okay, when is my knowledge of the environment even useful if I can fit a really good data-driven model? Okay, and I'm going to show you an example right after where some knowledge may be useful. Purely data-driven models also may fail, although I would argue these days they tend to be not necessarily emphasized as much as it used to be. One example where it was emphasized, you may know about it, it's more than 10 years ago now, it was Google Flu. So Google became very famous early on with its big data-based flu model. So they used the Google searches of people looking for flu to predict flu cases and the flu season. And it was quite successful when fit on past data, but then it was deployed and it did terribly. And that was the winter between 2012 and 2013. So these were slightly older and more naive algorithms. But a lot of the reason it failed is that it failed, for example, to capture the fact that when people Google, so it was based on a simple idea. If people are Googling flu, likely they're more sick. And so you get higher trends. But it failed to capture, and I don't know if you had lectures on causal inference, but just in case, I'll throw in the word. It failed to capture the counterfactual, where people are searching for flu because, for example, of a newspaper trend. And in that case, it became a hype. So people started looking for flu, but people were not that sick. And so the model dramatically failed. And that's because the model was purely data-driven and failed because it didn't have some simple knowledge of why people searched for what they searched. And it also didn't really cross-validate enough with the monitoring that the Center for Disease Control and Prevention was doing at the time. So this motivates us towards the best of both worlds. What if you could take the advantages of knowledge-based model and the advantages of data-driven models and put them together? And so this is what we call very generally knowledge-guided machine learning. This is from a literature review on knowledge-guided machine learning. This is a very simplistic view and a very easy way to define it. You have two axes here, the use of data from low to high, the use of scientific knowledge. And any model that makes enough use of data and knowledge can be called knowledge-guided. I've been arguing for quite some time that it's a design parameter that should be incorporated into any data-driven model you train, just like the number of trainable parameters and the degree of interpretability of your model should be. So that's in a review that I wrote, a review chapter in a textbook on clouds and climate, where I argue that you should not just think about the representation power of your algorithm, so how complex what it can describe can be via its number of trainable parameters, how interpretable it should be, but also how physics guided it should be. How much knowledge should you put? And there are clear extremes, right? If you put too much physical structure, then you're preventing yourself from any surprises. It's going to be too inflexible. It won't learn from data. But, using the right intermediate, maybe you can get a model that's flexible enough, but then constrained enough that in difficult cases, it will know to rely on knowledge. Difficult cases often being cases where we don't have much data, extremes, low data density regions, etc. Just a couple of definitions, since this is a summer school. If you want to see it from the most general to more specific, I would argue that the word alignment is maybe the most general you can come up with. And actually, it's one of ChatGPT's favorite words. So it's appearing more and more in scientific papers and machine learning papers to align. And AI alignment means that the behavior of the artificial intelligence algorithm that's being trained is consistent with the intended goals or ethical principles of the humans that train it. Within that, a particular case is knowledge-guided machine learning, where we use our own knowledge to guide the machine learning algorithm we developed. And I would argue physics-guided machine learning is even a specific case of that, where we use our own knowledge of physical processes to guide machine learning algorithms. And I've defined it, there's not a single definition. You can find it in a couple of really good reviews. They're listed on my website, on my GitHub. I try to gather all reviews in the field. So there's a couple of really good reviews on physics-guided machine learning. I think a reasonable definition is that it's the idea of adding physical structure to restrict the output of machine learning algorithms to physically plausible solutions. So often, and this also explains the success of machine learning, we could debate about this, we worked with underdetermined problems, especially when models start having a lot of trainable parameters. There's a lot of equally plausible models. There's a lot of different models that would lead to the right answer. And out of all of these models, some are plausible and some are not. If you just train an algorithm, it will pick one of them. And physics-guided machine learning can help you eliminate those that are physically inconsistent. And that's tricky to define, but I'm going to give a really simple example. Think about relative humidity. I'm assuming most of you are atmospheric scientists, so you know relative humidity is the ratio of the partial pressure of water vapor to its saturation value. And as such, it's defined as a positive variable, but its physically plausible range is between 0 and 1. So like it can't be below 0 because pressure is positive definite, and it's rarely above 1 because if it goes above 1, we are in supersaturation cases, and supersaturation tends to be quite rare, especially if you start looking at large spatial scales over long enough times. It's something that usually happens at the microphysical scales for brief moments. So what we know is that variable is mostly between 0 and 1, but it can be above 1 sometimes. So what could you do as a physicist if you were predicting relative humidity as a variable? Well, first you would say it shouldn't be negative. And people argue, okay, but don't put constraint on your machine learning algorithm. But I would argue against that. Like, why waste energy trying to learn negative relative humidity? Especially pretty much every algorithm has a simple option to predict only positive numbers. I'll give you an example in the case of neural networks. Right before your output layer, just put an activation function whose output domain is R plus, positive numbers. If you do that, you're good. The number you predict will be positive. Now, for the above 1 case, it's a lot trickier because that's when you start getting into the kind of debate you have when you do physics-guided machine learning. You don't necessarily want to fight against your data. And you know, some of your data samples are going to have values of relative humidity that are just a little bit above 1. But you want most of your samples to have relative humidity below 1. So instead of having such a hard constraint where you force a variable to be right above 0, what you could do is you could do a softer constraint where you really want to just encourage the algorithms to not go too much above 1. So again, I'll give you a really naive example. In the case of a neural network, what you could have is you could have a constraint that's going to pull relative humidity towards 1 until it reaches 1 and then it stops. So what you could do is you could just minimize a rectified linear unit of relative humidity minus 1 and add it as a term to your loss function, for example. And that would be an example of soft constraints. So you allow this constraint to be violated in some cases, but you're going to try to discourage the behavior. I'll give you some more concrete examples. I'm assuming you had some computer vision oriented talks. And so I'll talk about, for example, encoding invariance or equivariance in architectures. I'm going to give you examples, very common examples of hard constraints and soft constraints so that it's clear in your mind, for those of you who are less used to it. So invariance means that when you apply a transformation to the input, the output is unchanged. So to take a very simple computer vision example, imagine your CNN is tasked with identifying a dog. It's a very common example in machine learning. You have a lot of cute dogs and cute cats, and you have to say yes or no, is it a dog or a cat? Typically, if you have a detection algorithm like that, that works at the overall level, so you're just predicting two classes, dogs or cats, you want rotation you want your algorithm to be rotationally invariant. If I rotate a cute dog, it's still a cute dog. So it doesn't matter how much I rotate the dog, it always should predict dog. And so one layer, if we take convolutional neural networks as an example, that will do that if they're large enough, are pooling layers. So if you do a pooling layers, min or max pooling, this is rotationally invariant. If I rotate the image, its mean is not going to change. If I rotate the image, its max is not going to change. In contrast, imagine you took the exact same problem, but now you were doing what we call semantic segmentation. So to each pixel, you're going to assign a class. So for example, you're trying to find the dog pixels in the dog image. In that case, what you're looking for is what we would call equivariance. So if you rotate the input, I rotate the dog, you want to rotate the output, here are the pixels that tell you it's a dog, in the same way. And that convolutional layers, if you just do pure convolutional layers, tend to be rotation equivariant. There's a lot of theories on that, but one example from fluid mechanics, if you take Wang et al., show in that it was an older paper. Now there's a lot more papers that tell you how you can enforce different kinds of translational or rotational invariance or equivariance. They enforced strictly a magnitude equivariance, where the output would react by the same magnitude that the input. So if the flow was twice as intense, the result of the neural network was twice as intense. And this is an example of hard constraint. In contrast, a soft constraint would be what we typically use when we talked about physics-informed neural network. So you may have already noted that the definition I gave of physics-guided machine learning is much broader than what people typically called PIN, or physics-informed neural network. Often what people could call PIN is relatively specific. What they mean is usually neural network that takes spatiotemporal coordinate as input and then predict fields and then enforce as soft constraints conservation laws on these fields. So for example, imagine you're predicting your flow. You want to conserve mass, you want to conserve momentum. What you can do is set up a PIN, so physics-informed neural network, and then penalize the neural network for violating mass conservation or momentum conservation. And so in that case, what you will do is you will, for example, take the residual of the conservation equation of interest and add it to your loss function. And what that will do is that will encourage the neural networks to reduce the magnitude of that residual, hence conserving mass better, conserving momentum better. And this is soft because optimization is never perfect, and so you'll never truly get to zero. Okay, so that's the end of my short tutorial. I'll take questions about physics-guided machine learning, physics-informed neural networks, etc., before we get into a research example.
Questions from the audience, online or offline audience? Yes, we have a question.
Yeah, Hello, sir. I'm Dipan Chakraborty from IIT Kharagpur. So my question is, as far we saw that we can constrain we can apply physics in for constraining the laws. Can we apply physics to design the layers of the neural network?
Yeah, absolutely. And I'll get into it right after, I'll get into it in just a second. And I think it's in the reading I also put. You can, especially if you want to go for hard constraints, you can just build the neural network so as to enforce specific physical constraints. So it's exactly the example I gave for convolutional neural network. You can design, for example, a convolutional neural network to be perfectly rotationally equivariant. And now it's become mature enough that you can just find them online. There's entire libraries doing that. But what I'll show is that you can do that for all kind of physical constraints. So you can play that game for physical laws. You can play that game for specific types of invariances and equivariances. And as long as the final object remains differentiable, you can optimize it. So if you design the layer without breaking its differentiability, then you can usually be creative and enforce all kind of constraints. Of course, if these constraints are not satisfied in your data, you're going to have optimization problem because you'll be fighting against the values of your samples. But as long as it's not inconsistent with the data you're training with, I would argue we're still less creative than what we could be in how we design our neural networks. I don't know if that answers, if you want something more specific.
No. That's all. Thank you.
Any other question from the offline audience?
I have a question.
Okay, yes.
Yeah, so you
Yes,
mentioned
please.
that hydrology paper. Can you hear me?
Yeah.
Yeah, that hydrology paper, right? There was that comment that, through these machine learning tools, we see some scale-specific results, but the theory is not accessing scale-specific results. There's no scale-specific theory. So I was going to ask whether, have you encountered anything of that sort, and is there a way to address that? Can we use this neural net output to come up with some scale-specific theories? Are you going to show any of those examples?
Yeah. But it's in the second part of my talk. It's in the data-driven discovery part. So I don't know if I'll get to it, but in short, the idea is that if you are able, with a deep learning algorithm, to access a theory that's generalizable in some sense. So here they're talking about scale, so catchment across catchments, but I'll talk about generalizability across climates. You can do spatial generalizability, etc. Maybe you proved that there exists a model that generalizes across different regimes, and then you should be able to uncover it. And that's a lot of the work we do in the group. So, if you can build a model that has certain generalizability property, and that requires careful cross-validation and careful design, then you can prove that that model exists, and then with a bit of luck, you can distill it and bring it back to a human understandable level. That's not trivial, but it was in the reading. The distillation paper is exactly about that. So the idea would be you distill a machine learning model that's generalizable.
Cases where, when you apply things like equation discovery, you don't get nice or simple looking equations that seem physically realistic, but neural nets are able to do a good job. So that's
well, in equation discovery, you can get nice nice equations that are interpretable. I mean, I'll show one example. I just think they're much harder to find because, and that's proven, I think, in the more theoretical part of machine learning. It's much harder to discover a simple sparse model than a complex flexible model. So I would just argue that it's an extra step on top of deep learning. It's going further. It's harder. And so that's why typically we haven't seen enough examples of that. It's just because these are harder models to find. It's much easier to just throw a neural network at it, right? So, yeah.
Any other question from the offline audience? Yes, Shreyashi.
Hello, sir. So I'm Shreyashi. So in one of the slides, you have written that we add physical structure to restrict the ML output to physically plausible solutions. So,
Mhm.
so why haven't you written physically possible solution? Why it's plausible solutions?
You mean physically possible versus physically plausible?
Yeah, like the physics structure should constrain the solution of the any AI algorithm, but you have sent plausible solution. So by adding physics, could it go way off from what we expect?
Okay, so is a question about why the machine learning model would violate physics? So is it was a question about plausible versus possible?
So
Um,
I wanted to ask, when we impose a physical structure, so it should
mhm,
reduce the domain of solutions, but you have
right?
said it's physically plausible solution. So does that mean that it even after imposing some physical structure, it can be way off from the solution that we expect?
Yeah, I mean, especially in cases that are not fully solved and cases that are underdetermined, you have a set of solutions. And to me, it's restricting that set. So if you want to see it from a strict Bayesian perspective, you could, say, okay, I have a large set of possible models. And then within that, I have physically implausible one and physically plausible one. If I put enough constraints, I can only search models, search solution functions within the subset that's physically plausible. Now, that subset may still contain a lot of different models, and some of them may be better than others. But usually, in very, very often, we are in underdetermined case, or if you like, the other word that's used in some subfields, like we have a lot of equifinality, where we have a hard time distinguishing what the exact best model is. We have a lot of equally plausible models. And then within these equally plausible models, some of them are physical and some of them are not. So actually using physics helps you prune out models quite a bit often. And the reason I use plausible and not possible, just in case, I'm not sure whether part of your question included that, but it's just some of the physical knowledge is exact, but actually very little of it is exact. If you look at all of the knowledge we've accumulated, for example, in climate science more generally. And so harder knowledge, like exact knowledge would tell you the possible solutions, and then softer knowledge will tell you the plausible solution. And I argue that all kind of knowledge, if it's proper knowledge, should be able to help you find better solutions. I don't know if that answers your question.
Yes, sir. The last part actually clarified. Thank you.
Okay,
Sir.
okay, cool.
Anyone else? Yes, one more.
Hello, sir. This is Nishant from IITM Pune. Sir, actually, we know in general, and we also saw in the previous talk, that one of the limitations of machine learning has been in extrapolation. So my question is, does embedding physics genuinely improve generalization to unseen climate scenarios or extreme events? That is like, can we use...
Yeah, that's the exact... sorry, I'll let you finish your question first.
I mean, that physics-guided machine learning, can it help to improve extrapolation beyond the training domain?
Yeah. So that's exactly the point two on this slide that I'll talk about. I'll present the climate invariant machine learning paper. It's also linked as one of the readings. Not all physical model. So I think that's tricky because and machine learning papers often overclaim, right? Some papers will have you believe that any physical knowledge improves extrapolation. That's not true, in my opinion. It's maybe true for extremely low dimensional system where adding knowledge gives you almost the entire solution. So, if you have a 5-dimensional system and you give three constraint equations, then, it's a free lunch type of situation because you give so much of the answer. But often we work with much more complex systems and our knowledge is much lower dimensional than the system we try to model. And in that case, sometimes it can help generalization, sometimes not.
Okay, thank you, sir. Sir, just one more question.
Yeah.
Like, I had a basic question that generally in real life, when we use physics, it's sort of an approximation, right? We work in ideal conditions. So the question is like, how do we incorporate this partial physics or like idealized physics to like our machine learning models? wouldn't we'll have to deal with conflicting or incomplete physics?
Yeah, no, it's a very good question. And I'm going to mostly dodge that question in the next section where I'll present exact knowledge situations. But in many cases, the knowledge is approximate. And in that case, I can give you a very pragmatic response. What I always recommend people to do is to just go in your training data and actually check how good that knowledge is, right? You have access to your training data. You can exactly measure how good this piece of knowledge you want to use is, whether it's an equation, a transformation, etc. There's usually a way to measure it. Imagine in your training data, you find that, it's good up to an uncertainty level, let's call it P. Then what you can do is you should probably not make it a hard constraints if there's many cases where it's not verified. You should probably make it a soft constraints. So for example, something you could do is you could have a soft constraint that turns off once you reach that uncertainty level. And that way, you explicitly take into account the fact that you have uncertainty in your knowledge. And I think that's something that's we're not yet at the stage where I'm seeing that done too much. I'm seeing a lot of, we're more in cases where we use knowledge that is almost perfectly verified in the training data. Approximate knowledge that helps a bit with some, uncertainty around knowledge, like being able to properly describe the uncertainty associated with knowledge and using that very explicitly. I've seen it used in Bayesian framework, but in deep learning, I don't think it's used as much. But I think the simplest way would be just to have a loss function term that turns off once it goes below the level where you're not certain about your knowledge anymore.
Okay, thank you, sir.
I don't know if that answered that second part. That's a tricky part. It's actually a research question. I don't think it's properly solved if you look at the literature.
Okay, thank you, sir.
Okay. There is a question from the online audience. So Moti Gupta is writing, is there a reason for using convex combination in soft constraint loss? How do we design hard constraints? And also, would physics limit our model to find more interesting patterns? Should we start with physics loss and then remove it later in training?
Okay.
Maybe we can go one at a time.
Okay, so third question. I'll start from the bottom because that's the one I have on my screen. The third one, I would argue, it depends on the type of knowledge you're trying to enforce. In one slide, I'll show you that, for example, you can enforce the ideal gas law, right? So if you enforce the ideal gas law, that's exact knowledge. You're not really interested in solutions that don't respect the ideal gas law, except in extremely specific pressure temperature conditions that we don't really observe on Earth, or at least not at the standard scales. And so in that case, you shouldn't remove you don't have to remove the physics loss because it's true, you want it to be true in your solution. In cases, well, actually it's related to the question that was just asked, right? In cases where the knowledge is approximate and you don't want to overly constrain your model, either just don't enforce it, right? If it's approximate knowledge, maybe you want to improve upon it. So maybe you should just not enforce it and see what you learn with a neural network. Or as they say, enforce it to a given level and then remove it, set it to 0. Going up, how do we design hard constraints? So many ways. I'll give you an example in a second. That's quite simple, a relatively naive way of doing it. And then if you want more ways, I like Paula Harder's JMLR review on hard constraint downscaling, where she shows not just additive layers, but also multiplicative layers. And I think this is nice. There's so many ways of doing it, but I think there are some simple ways that work well, and she reviews them. Is there a reason for using convex combination in soft constraint loss? Okay, I'm not sure what is meant by convex combination. I think all I argued is that you should you should put a norm of the residual so that it's well behaved. It's positive, definite, and it goes down when you minimize the residual. But maybe I miss what is meant by convex combination. Because I don't think I made any kind of convexity argument here, but maybe I'm
Okay, thanks, Tom. I think we
I mean,
can carry on.
or at least if you do stochastic gradient descent, you don't really have to assume, like some optimization algorithms require convexity, but stochastic gradient descent usually doesn't care as much. I don't know if that answers the question. But,
Okay,
maybe
I think, Tom, you can carry on maybe with that talk.
Okay, fantastic. So now I'll switch to a simple example where I compare soft and hard constraints. So let's get started. The problem we motivated to solve is a weather forecasting problem. So here I'm showing you a beautiful photo of Locarno. That's where one of the Meteo Swiss agency is in Switzerland. It's in the southern part. You have usually beautiful storms coming on the lake. And we want to predict them. And so what do we usually do? We run dynamical forecast. And so this is a picture of the old and now the new grid of the weather forecasting model that's used operationally by Meteo Swiss in Switzerland. So we switch from Cosmo to a specific version of Icon. But you can see that no matter what the grid is, if you want a prediction at the local scale, you'll never quite be covered by your mesh. Usually, maybe you'll land somewhere in the middle of it. And so these models don't have the required scale for computational reasons to give you exact prediction at the location you want. And so that's where post-processing comes in. In Meteo Swiss, we have a very nice app where we read our forecast from Meteo Swiss. And the numbers that you see on the app are post-process, which means they went through a mapping from model, so in that case, dynamical forecast model output to observations. And so based on past observations, we've trained, I say we because we do some post-processing models in the lab, but in that case, it's really Meteo Swiss for the app, trained a statistical data-driven model linking all the past output of your dynamical forecast model to observations, so that whatever you read is informed by local observation at your exact village. Even if it's trapped between the specific mountains, that means that the precipitation situation is strange and right above the lake. Where deep learning comes in is that traditionally, these post-processing models are a bunch of multiple linear regression. People used to train sometimes one per station, one per month of the year. And so you have this huge collection of linear models. And what deep learning can do is you can just, embed the time of the year, you can embed the station ID, and now you just have one model that post-processes the entire dynamical model output at once and gives you observationally informed forecasts. Now, it's a statistical model, so it's going to take shortcuts. And one of the shortcuts it takes is violating physical laws. More specifically, we are going to be looking at post-processing models targeting surface observations of temperature, dew point temperature. That's the temperature you need to adiabatically cool a parcel to until you reach the saturation point. So it's smaller than the temperature. Surface pressure, relative humidity, and then mixing ratio, which is the ratio of water vapor density to dry air density. And what we have exact knowledge of how these variables are related locally. So we have the ideal gas law, which holds under the conditions that we experience on Earth, that allows you to relate this pressure to the water vapor mixing ratio via molar mass ratios and the saturation, the partial pressure of water vapor. And then we have the Clausius-Clapeyron equation that if you integrate it, so here I'm using what we call the Augustin-Roche equation, which is one possible integral of Clausius-Clapeyron that's used operationally by Meteo Swiss. You can express this partial pressure of water vapor as a function of the dew point temperature. And so now I have two equations that I can rearrange to relate these 5 variables. So these 5 variables are not truly independent. If I have 3, I can deduct the other 2 exactly. Now, if I calculate the residuals here, if I scatter the residuals of these conservation equations, what I get is errors of the order of 10%. So even if I train a deep learning model that does very well, it will typically take shortcuts and violate these laws that we know to be exact in the data as well by up to 10%. Here I'll be tracking on the right-hand side normalized mean squared error. So higher up is worse, lower down is better. This is the error on several folds, that's why we get uncertainty, of an unconstrained model. But what we can do is first try soft constraints. And so the reason we usually start with soft constraints is that it's a lot easier than changing the architecture. So if you have knowledge and you just want to make it work a bit better, a soft constraint is extremely easy to implement. You just add a norm of your residuals, and you weight it appropriately. Ideally, you use the same units as you used for your loss, so that these terms are comparable in magnitude, and you don't have to think too hard about your base value for lambda. And then, by encouraging the neural network to better respect the ideal gas law and the Clausius-Clapeyron equation, we already reduce the residual by quite a bit. But now you may say, it's not enough. I want my loss to be exactly enforced. I want the residual to be 0 to within mission precision. So what you can do, and that's to answer a question about, okay, but how do you actually enforce these conservation laws? What you can do is you can predict, okay, I have 5 variables, 2 constraints. What I can do is I can predict 3 variables and then calculate the remaining 2 using the constraints. But now the trick is to do it inside the neural network. So, if you're using PyTorch, you write a torch layer. If you're using TensorFlow, you write a custom TensorFlow layer. Just make the whole thing differentiable. And then, as you optimize your neural network, here, the weights and biases will implicitly know about these constraints. And by design, you're going to enforce these physical laws to within machine precision. And in that case, so it's a bit of a free lunch case. So just going back, yellow was the loss constraint. Typically what happened is that when you add a term in the loss function, sorry, I'm trying to go back to when we had the soft constraint. You're going to have a competition between these 2 terms. And that explains the degradation in performance that we see for the soft constraints. In contrast, if I do it as a hard constraint, here I enforce it to within mission precision and I decrease the error, especially in cases where I don't have too many samples. So this is what I would call a quote-unquote free lunch case, because it's a low-dimensional system. I have 5 variables, I give 2 constraints, everything works together. This model is also more generalizable, so if we go to very moist or very dry situation or very low sample situations, it performs better. This is using a much more general method that we published in Physical Review Letters 2 years before, where you can do it for any analytic constraints you can write down or write as a differentiable algorithm. It can even be nonlinear constraints. You can use this very simple idea of predicting, instead of predicting P output, predicting P minus N outputs, where N is your number of constraints, and writing them inside your neural network. And then optimizing the entire thing. It's very general. It can work in all kind of engineering and physics field, which is why we wrote it in PRL. But now for those of you who already understood how this all works, it's not the only way of doing it, right? Here is, if you want an additive residual approach, you could also multiply the variables to make sure the constraints are enforced, which is why I recommended the Paula Harder et al. Paper, where they also talk about multiplicative constraints. Now, let's take a few steps back and think about what we just saw. Here, it's a case where if you have exact knowledge of atmospheric physics, it can be chemistry, it can be any knowledge you can write in equation form or in algorithmic form, you may enforce it. And you may use hard constraints to exactly enforce it if you're not fighting against your data. So far, so good. I don't know if I want to take questions or if I can... maybe this is a good time to take questions, because then I'll switch to a slightly different theme and I'll talk about hybrid AI climate modeling. Are there still questions on this theme?
Sure. Any questions from the offline audience in the hall? Yes,
If
there's a
not,
question.
oh, there's a question.
There's-
Okay.
Yes, please. Any questions in the online audience?
Okay,
Okay,
I'll
if not,
keep going.
we can carry on.
Okay, so we were talking about generalizability, and you asked me about generalizability. And what I want to show is there are cases where we don't necessarily have exact knowledge of the system we're trying to model, but we can still help the algorithm. And in that case, I can show, I'm going to show how knowledge of atmospheric physics can be used to design feature transformation that helps generalizability. So cases where we don't have a purely exact knowledge, but you can still gain a lot by using knowledge. But before that, I want to give a second short tutorial, because we're because it's a summer school, and I want to give a tutorial about hybrid AI climate modeling, because I think it's a topic that's going to be more and more important as the years come. So why do we even care about combining of physical models with some data-driven components? And why do I think, at least that's my opinion, that in the future, more and more Earth system models are just going to be hybrid. They'll have data-driven components and they'll have physical components. I'm a cloud physicist, and one of the largest uncertainties, if you know how much greenhouse gas and aerosols humans are emitting, which is far from easy, but given this knowledge, one of the largest uncertainty we have when we make long-term atmospheric projections is how clouds behave, and especially what we call separate clouds. So it's clouds at a spatial resolution below that of the mesh used by the climate model to simulate the primitive equations. And I like to use this example. You'll see I love North American movies from storm chasers. This makes a very good case that the dust storm is extreme. This dust storm that you see right now, which is a convective storm, is extremely good at transporting dust vertically. But it's not just transporting dust, it's transporting any traces that's currently in the atmosphere. So just like it's transporting dust, it's transporting temperature, it's transporting water vapor, but what you can also notice is how small it is in radius. So it's a pretty small storm. No way it's going to be resolved by our traditional climate models or any climate models that is currently used for CMAP or even high-res MIP or even high-res MIP v2. Yet it's going to be an order 1 contributor in the vertical transport of tracers, which is why we have to parameterize it. And so in Earth system models that are not explicitly simulated at the grid level are typically parameterized. So this is a schematic from the European Center for Medium Range Weather Forecasting, and it gives a good overview of atmospheric parameterization, from atmospheric chemistry to subgrid scale drive parameterization, which are really important for momentum, to cloud parameterization that matter a lot for momentum a bit, but also for thermodynamic quantities mostly. Now, if I take the typical grid of a climate model, and I take this beautiful picture from a plane, and I coarsen it to the kind of level you would see in a climate model, this is how clouds really look like climate models. So you can imagine why we have just no hope of explicitly simulating in our climate models, at least if you build them traditionally, these cloud processes that are so important for the budget of heat, for the budget of momentum, and even for the budget of mass. And you want these budgets to be well respected and properly simulated if you're about to integrate your model for 100, 500 years with a tiny little bit of forcing on top. So what can we do? Traditionally, so what machine learning parameterizations do is they take a very data-driven approach. They say, if you have data, imagine field campaign data. Interestingly, field campaign data from the tropics informed heavily some of the earliest convective parameterizations we had. You can also take high fidelity model data. So, short-lived model runs, I'll show you later, that are too expensive to be run for hundreds of years, but they are high fidelity, so you can learn a lot from them. And you can take a brute force machine learning approach. So you say, okay, the goal of the parameterization is just to output fluxes given climate condition. So all I'm going to do is I'm going to take the grid scale information, and I'm going to collect it in a vector X. I'm going to take the target fluxes, I'll collect it in a vector Y, and I'm just going to learn to map one to the other. And that's quite different from traditional parameterizations that were done more semi-empirically. So you can't possibly summarize a single way of how parameterizations have been designed in the past 50 years. But usually what good semi-empirical parameterizations do is they'll start from asymptotic limits. So they'll say, okay, in that extreme, the atmosphere behaves this way. In the other extreme, the atmosphere behaves another way. And then they'll kind of put lines of function in between these asymptotes, depending on how they're framed. And then they'll use a little bit of observational data to constrain that. But you can see that if you design a parameterization that way, it's going to be suboptimal, which is why machine learning parameterization, in terms of raw performance, have been crushing semi-empirical parameterization if you evaluate them given data that you trust. And what is data that you trust? And that's a good question. We're not yet at the stage where we routinely inform our data-driven parameterizations with observations. So a lot of what the earlier work has done is train these parameterizations on high-fidelity storm resolution data. So you may be aware, for now 10 to 20 years, there's been the emergence of kilometer-scale atmospheric models, where because the mesh is fine enough, convection doesn't have to be parameterized, at least deep convection. And so then you can explicitly simulate how deep convection interacts with the atmosphere across the multiple scales covered on Earth. The video I'm showing, and I don't know how well it's rendering because the connection from Switzerland to India may not be optimal. Is the movie okay? I'm going to assume it's fine. This is a lot of PR, right? This is a video of the latest ICON kilometer scale simulations. But for the credit, they did run the Diamond intercomparison experiment, and that's the best data repository we have of kilometer scale simulations. These models are nowhere ready to be used for long-term climate projections, but they are ready for training neural networks, and we've been doing it for a couple of years, where you can use that data, feed it through neural networks, and even though you're not able to run this for hundreds and hundreds of years, the neural networks can mimic the effect of a storm resolution simulation in a coarser climate model that you can run for hundreds of years. And that's the idea behind hybrid AI climate modeling. There are few quirks in practice. It's not as easy as it sounds when you just look at the video and you say, okay, great, I'm just going to build the neural network and it's just going to learn all of this magically. You need to use this high fidelity, high resolution data from the perspective of a coarse model that may have never accessed these exact regimes anyways. And so what we use is some form of coarse graining or filtering to bring the high resolution data back to the perspective of what a coarser model would see. This step is not trivial, and actually, depending on how you do it, you may change the end result. That could be a debate for another day. What I want to say, though, is now for a couple of years, the field and the techniques have been mature enough that we have been able to routinely train deep learning models on high fidelity model data to train these data-driven parameterizations, and then put them back in climate models so that then you get a coupled simulation where it's not like atmosphere-ocean coupling. Here I'm talking about the coupling between the dynamical core of the model and a neural network that mimics subgrid scale effects. Here, I'm showing you how well these neural networks do based on a proof of concept paper in a realistic geography setting led by Griffin Moores. He's the first PhD student I was lucky to work with from beginning to end when I was a project scientist. He's at MIT now, still an expert in data-driven parameterizations. On the left is 600 hectopascal convective moistening. So this is the amount of water vapor changes that occur due to subgrid effects. On the right is just precipitation in log scale. And what you can see is, except if you blink, I mean, you can see that the neural network here is deterministic. It has a bit of a smoothing effect, but overall it's doing an excellent job, at least offline, at reproducing the main patterns that we see in our truth, which in that case is the storm resolving models. And this is just one example. This was back in 2021, but now simulations are really flourishing. This is a paper from a collaboration led by Klima at Caltech, where Costa Christopoulos was able to train an entrainment-detrainment parameterizations online. So training after coupling the neural network to the dynamical core of the model so that you can directly train to optimize emergent climate statistics. I think the neural GCM is the best example from Google of something that's fully differentiable, fully trained online. At least it got a lot of press. It's mostly used for and ready for weather forecasting, but the Google team is working hard to make it also a robust climate model. We've also reached the stage where this idea of data-driven parameterization was popular enough that as a group, I was just like a small part of a gigantic team, we were able to create an entire benchmark data sets for that specific purpose called ClimSim. And it had a Kaggle competition with up to $50,000 for the winner. There was a winner. We discovered a lot of, that was part of the review panel. We discovered insane, crazy solutions that we would never have thought of before. All of that to say, we do really have a lot of options now. We are at this stage where we have more and more machine learning parameterizations. And because there's so much going on, I'm advertising it because it's a resource that I've spent a lot of time developing and I will keep developing. There are a lot of hybrid Earth system models now. And so I keep all of them on a living review on GitHub. You can just use that link. It's Beucler, my username /hybrid ESM. And you'll see that there's a lot of different models that combine these data-driven parameterization with neural networks, data-driven parameterization with a dynamical core, or do some kind of climate emulation so that you have climate emulators that are very cheap, yet data-driven. And there's a lot of different ones. And they can all be grouped under the general umbrella. Obviously, it's too new for it to be a general universally accepted definition, but they can all be grouped under the general umbrella of hybrid AI climate models. This is another picture from Nature Review led by Veronika Ehring, where she shows, okay, this is maybe the dream hybrid model where you have all these different Earth system processes and neural networks for each of them that can be accelerated or better model. So you may ask yourself, why are hybrid AI climate models not routine by now? If they're cheaper, if they better describe high fidelity data, why isn't CMAP7 all hybrid AI climate models? And I'm going to leave that question up as I take questions now. But question could also be comment, right? If you have thoughts on why they're not routine by now, you can incorporate it in your question and we can discuss. So maybe this is a good time to finish that second short tutorials. I hope I made the point that hybrid AI Earth system models are flourishing. There's a lot of potential, but now we may ask ourselves, why are we not there yet?
Okay, questions in the audience? Yes. Yes, please, Dipan.
Sir, my question is, what is the computational aspect of these hybrid climate models? Like how they are, if they are more computationally expensive or less computationally expensive than the fully data-driven deep learning, deep neural networks are there?
Okay, so that's a very good question. And the first order answer, just to make it very easy at first, because the full answer is actually quite complicated. The easy answer is kilometer scale physics-based model are incredibly expensive. You cannot possibly run them unless you have hundreds, sometimes of thousands of CPUs. Purely data-driven models, once trained, neural networks, is just a bunch of matrix multiplication thrown into activation functions. If you have the right hardware, like GPUs or even TPUs, they're extremely fast. You can run a hybrid climate, if it's a purely neural network-based climate model, like ACE, you can run it on one or even a couple of GPUs. Hybrid models live somewhere in between. So that's a bit the idea. The idea is maybe you want to keep your dynamical core based on physics, and you want to learn everything that's uncertain from data. And in that case, you'll get an intermediate cost. So that's a bit the idea of training your neural networks on these high fidelity simulations, is that once you replace the cost of zooming in by just staying maybe at a horizontal grid spacing of, let's say, around 100 kilometer. And as you may know, there's a cubic computational scaling between different resolutions. So it goes quite fast, quite high. And then you replace all the uncertain processes with a neural network and you keep the model coarse. Then you can accelerate by a factor of, 100, for example, or 1,000. But the research is still out there, because depending on the data-driven model you put in, it's going to cost more or less. And it may be handled more or less optimally depending on the architecture. So, sorry, that's a long answer, and it's actually a research topic, but the short answer is pure neural networks super cheap, kilometer scale model extremely expensive, hybrid model somewhere in the middle depending on how you design it.
Thank you. I have one more question. Like, do we always for this kind of problems? Do we always need to go for hybrid models or physics-informed neural network, or sometimes we can stick with the direct data-driven model also?
Like just be completely data-driven, no physics.
Completely data-driven. So, I mean, do we always need to go for a physics-informed or physics-based or?
So this is why I advertise this review a bit. You'll see there's all kinds. And so, for example, the first case here, ACES, is purely data-driven. There's some minimal, it's built in a way that's physical enough that you can force it. So it's built cleverly to conserve mass and energy so that you can actually force it if you want to understand the response of the climate to CO2. But ACE is an example where it's pretty much purely data-driven. It's only physical in the variables it uses and how it conserves quantities. The camulator, I think, is mostly like ACE. C-brain is closer to what I showed, so it's hybrid. Klima is one step towards physics, so it's quite physically constrained. Like it's mostly, one could argue different things, but I would argue it's mostly physical models with some data-driven components at the exact place where we don't have precise knowledge, etc. So you can just look at this review, peruse it, and don't hesitate to make a git pull request if you think some information is missing, and you'll see the incredible diversity of hybrid Earth system models out there. And most of them are recent, right? This is all over the past couple of years. And we have the entire spectrum.
Thank you. Thank you very much.
Any other question? Yes. Next. Nishant.
Yeah, sir. Actually, like we talked about adding physics-based constants like parameterization and all in our loss function. So, like my question is, like in cloud microphysics, the parameterization itself is sort of uncertain. So, should we treat them as truth in the loss function? Because like if like the physics which we are using is itself uncertain or approx, does it even make sense to treat them as a rigid constant in ML models, or should we allow the ML models to learn and correct this physics? What should be the
Yes, so most hybrid models take the second approach. Indeed, for the reason you said is that emulating microphysical schemes, especially the more traditional bulk microphysical schemes, is not often worth it because we know they're wrong, or at least we know they're imperfect. And so you can replace them with machine learning trained on different aspects. So the models that are trained online end to end, you'll directly optimize the parameterization to produce the best climate statistics. So you're really not making any assumption. You're just saying, okay, my model should produce the best climate statistics. Or you can take intermediate steps. For example, people will argue bin microphysical schemes are very good, or at least better. I mean, for sure they're better than bulk, but they're more expensive. So then you can emulate bin microphysics. Or you can take yet another approach, right? You can say, I know what the tendencies of high fidelity models are, or observations where I trust that the microphysical processes are properly represented, or at least their emergent statistics, and I'll train on that. So there's a lot of different approaches. I think if you look at machine learning for microphysics, there's quite a few good papers. I really like Hugh Morrison's paper, like Morrison et al. There's an excellent review on the challenges of microphysics that makes a very informed point about why data-driven microphysical parameterizations may become more common. But why? Not just like, okay, we should replace everything with machine learning, but pinpointing the exact challenges that justify such approaches. But to summarize, yeah, I don't think anyone would emulate bulk microphysical schemes, for example, except if they were just doing a proof of concept.
Okay, thank you, sir.
Does that answer the question?
Yes, sir.
Okay.
Hi, sir. I have a question.
Yeah.
It's more of a general question than very technical. So we develop these machine learning parameterizations for a particular model, particular ESM. Like for example, if we hybridize a particular ESM, like the CAN ESM or whatever, so how about the cross compatibility? I mean, we hybridize one particular ESM, such as the maybe CAN ESM or any other ESM. How about the cross compatibility of this particular parameterization to other ESMs? Does that work that way, or do we have to hybridize each ESM separately?
Okay, so the first order answer is we have to hybridize. So it's a topic I think a lot about. It's a challenge I really like, right? Like, can we, when we do this work, can we make it useful to just more than one particular model? And sadly, the first order answer is yes. You have to work per model for the simple reason that models don't divide their parameterizations the same way. So just, I'll give you a really simple example. If you have a model that puts deep convection and shallow convection in separate parameterizations, and a model that unifies both, you're never going to be able to use your shallow convective parameterization in the model that unifies both. Similarly, if some models use different prognostic variables in their parameterization, it's so they're going to have different inputs and outputs, and they want to output like, imagine you have a model that will output some kind of static energy and one that will just output water species. You'll never be able to use one for the other just because they don't even work on the same variables. So unfortunately, the first answer, once you start digging into models, you realize they're built quite differently, and you'll realize that the first order answer is no. Now, I'm interested in this problem, and I desperately want to find examples where our knowledge is transferable. Just for the reason that I think that's probably why you were asking the question as well. I don't love the idea of having 100 different data-driven parameterizations, one per model, right? It feels cumbersome. And so we've been working on this for convection, for example, where a lot of different models have similar inputs, outputs, so that you can hope to plug in the convective parameterization from one model in another model. And it's work in progress, but we have promising results. For example, taking ClimSim that was developed with a model from the Department of Energy, E3SM, and we're trying to plug that convective parameterization in ICON. And what I can say is the first challenge is that your variables don't even live in the same statistical domain. So what you need is really robust uncertainty quantification. So if you're going to use knowledge from like that's more linked to one model and put it in a different model, you want that parameterization to tell you when it's right or wrong. That's one of the first challenge. Another challenge is maybe aligning statistical domains. So the variables are going to have slightly different values. So you want your model to be able to handle that. But in summary, just to give you the answer, the first order answer is no, just because the wiring is not right. The second order answer is I think there's some research that can be done in that space and we're doing it, but it's very hard because you need proper uncertainty quantification and you need to be robust to large statistical domain shifts.
Thank you. Thank you so much.
There are a couple of questions online. So first
Yeah.
question by Balakrishnan. Is there a hybrid model to produce reanalysis data like ERA5? If it's not there, why not? And if it is there, then will it provide a less biased data set?
I'll start by if it's not there, because I don't think we have a hybrid model that produces a data set that's more reliable than ERA5. We have ERA5 emulators, and these are the AI weather prediction model or neural weather models, but to my knowledge, we don't have a hybrid model producing a better reanalysis. The answer is, if not, for me, it's just what data would we train it on? We don't really have a global observational data set that's significantly better, that's gridded in a way that you can improve ERA5, because ERA5 is a product of data assimilation, right? You would take IFS, and using a very diverse set of observations, you assimilate these observations into IFS, and then you produce ERA5. But once you have, I guess maybe I'm misunderstanding the question. In theory, it's possible. In practice, I think you'll have a hard time beating ERA5. But if you just wanted to produce a reanalysis, I don't think anything would prevent you from doing that. By building an emulator of the global atmosphere and then assimilating some observations into it. And that I would point that person to recent work on machine learning for data assimilation. Is probably the kind of literature they want to look into. And maybe a little more the weather side of things, because on the weather side, data-driven weather forecasting, they've produced really nice model that emulate reanalysis, but also do end-to-end observation forecasting. And these models facilitate data assimilation by quite a bit. So there's these models, and there's also new machine learning techniques to better assimilate data. So I think in that space, you could have a hybrid model producing reanalysis. Now, I don't know why you would necessarily want this model to be hybrid. I don't know which physical components you would keep. So sorry, I don't have a precise answer other than, to my knowledge, it doesn't really exist yet, but it's probably possible. It hasn't been done though.
Okay, thanks. And the second question from Moti Gupta again is there is this hierarchy of various sub-processes of Earth system models like radiation,
Yes.
hydrological, ocean,
Like this.
etc. Now, the question is, can neural network discover better taxonomy of various sub-processes? And since more sub-processes lead to more error accumulation,
Yeah, that's a really good question. Oh, sorry. No, you're right. You were reading it for the in-person audience. Sorry. I'll let you finish.
Yeah. Okay, so I'll just start from once again. One thing I have seen a hierarchy of sub processes like radiation, hydrological, ocean, etc. are different neural networks translated from their ESM counterparts. Now, can neural network discover better taxonomy of sub processes? And since more sub processes lead to more error accumulation, I suppose a single big model for everything would also not be a good idea. So, what is your opinion on it? That's the question.
My opinion is that it's a really, really good question. And I'm biased because this is, I think, an important research question that we need to investigate in the future. There's this fundamental assumption that most Earth system models make is modularity. So we assume that the Earth system can be decomposed into components that we can optimize separately. And it's really a profound assumption because if you think even in the way we organize the scientific community, we work under the implicit assumption that, for example, chemists can go optimize the chemistry models, then physical oceanographers can go optimize the physical oceanography model. And that somehow when we put all of this together and optimize these subgrid processes on the individual processes they correspond to, the whole will be more optimal. And implicitly, we assume this for several reasons: tractability, the fact that you can assimilate observations of different nature in different parts of the model. And yeah, there's a lot of other underlying reasons, but it's really interesting because we organize the scientific community in a way that's consistent as well. So it's really an overarching assumption that we kind of made, or that was made for us. From a statistical perspective, you could think maybe that's a form of regularization too, which is interesting. But you can question that, right? You can say, okay, what if I had some kind of gigantic data set? And I mean, tech companies are making such arguments, right? I can just collect data everywhere. And then I don't need to go optimize one parameterization at a time. So for example, if you look at how the neural GCM is structured, I don't have the equations here, but it doesn't have parameterization per process. It has, in a sense, parameterization per prognostic variable. So it will say, okay, I'm going to integrate 10 prognostic variables in time, and the parameterization is going to learn one forcing on the right-hand side of each prognostic variable. And then the only real separation, if you even think they're separated, because it's going to be the same neural network in the end, is per prognostic variables. And maybe that's more optimal in a way. Now, one thing that's interesting philosophically is actually you cannot truly get away with that, because then the next question is, how do you force the model? So now imagine humans start emitting, I don't know, maybe suddenly like Mumbai emissions drop by half, and suddenly, I don't know, the US start emitting twice as much. And that happens tomorrow. We've never seen it before. We want our climate model to give a realistic response to a scenario like that. Okay, now which variables do you perturb and how do you enforce something like this? And that's when you realize that you do need your climate model to be compartmentalized in a way that allows it to respond to forcing. So you can't do anything with it. So you need at least probably one separated radiative parameterization that translates into some form of heating. Same thing, if you want to talk about the effect of land use on the climate, you need to be able to force that in some way. And so, sorry, that's a long response, but to a question that I think is very interesting is, I think there's a minimal necessary configuration for hybrid Earth system models to make sense. I don't think there's a consensus on what that minimum formulation is, but if you go to the review, I think models like ACE or Camulator that are really trying to be like just a neural network that you can use as a climate model, they go as far as they can towards that simple limit. So by looking at how a model like ACE is formulated, and ACE can be forced, and there is a paper where ACE responds to CO2 from the AI2 team, then I think that gives you a sense of the minimum amount of modularity you need to simulate realistic responses to forcings. Sorry, I went on for a bit, but I think this is a really fundamental question. And this is why the neural GCM, by the way, cannot be used right now. It's because there's no simple way to force it.
Okay, thanks, Tom, for the responses. So I think we can now carry on with the remaining of your talk.
Thank you. And there's no way I'll get to the end of my talk. So I think I'm mostly going to do the physics-guided machine learning part. And then I can always send you the slides if you want the second part of data-driven discovery, and you also have the link to the paper. We'll see how far we get with the time we have. So now I want to show you an example in a hybrid AI climate model. So in the one I just showed you, where you can use approximate knowledge to help you model better generalized to unseen scenarios. So I left you with that question. Why are hybrid AI climate models not routine by now? Well, it's because they're imperfect. Someone talked about extrapolation. If you're not careful, there's no reason for data-driven models to generalize well. I'll make the point with the example of climate change. This is a bit of an exaggeration for dramatic effect, but what happens if you train and validate a neural network on a cold simulation and then test it on a warm simulation? And again, these are exaggerated images for illustrative purpose, but I do want to break my model. As a physicist, I want to test its limits. I really love the new papers, and I should have checked the speaker that was right before me, but like if they talk to you about extrapolation, that's one of my favorite topics. I'm really happy that the community is investigating this more and more. Here I'm going to do on purpose, I'm going to warm the climate by 8 Kelvin, not because I think the surface is going to warm by 8 Kelvin, because I think that's a good way of exposing the errors that these data-driven models may make when exposed to warmer climates. So I'm going to go back to these subgrid scale parameterizations, the neural network one. This is a typical sample where they have to make prediction. So on the left is moistening, on the right is heating. This is how much water vapor is redistributed at every single level of the atmosphere. This is how much heat is redistributed by the atmosphere on the right-hand side. And I'm going to take models that work well. So imagine they're pretty close to these lines, and then I'm going to warm the climate, and that's in the climate invariant machine learning paper. Now these models can break by a lot. They can break so much, and that's because of, we can discuss this more of why mathematically that happens. It's linked to activation functions, but if I expose them to this new climate that's hotter, that's 8 Kelvin warmer, they can make errors by a factor of 10. I mean, insane errors. You will fully break your model. And so now if I think back from the mapping perspective, remember that there's no magic in machine learning really, especially in a supervised context. What you're doing is you're approximating a mapping from data. Specifically in the case of a subgrid scale parameterization, what you're doing is you're mapping the core scale climate to the response by subgrid scale processes. And to give you a bit of a sense of why this error happens in a warmer climate, I'm showing you the histograms of different variables. If you're into statistics, you can think of this as the marginal distributions of these different variables. So this is moisture in the cold and in the warm climate. Temperature, surface fluxes, and these are the distribution of the subgrid scale fluxes they're trying to predict. What I just showed you suggests that this mapping is not the same in the cold and the future climate. So training in the present climate will not give you a mapping that works in the future. In other words, that mapping is not climate invariant. And why is that? It's because if you look at variables such as specific humidity, which is the mass concentration of water vapor in the atmosphere, because of if you warm the surface by 8 Kelvin, because of Clausius-Clapeyron, the air can hold more water vapor per unit mass, and it can hold it more in following a function that increases near exponentially with temperature. And so the neural network in the warm climate is exposed to value of moisture it has never seen during its training. So it has to make up an answer. But then we know how specific humidity is increases in response to the Clausius-Clapeyron equation. You can just form relative humidity, which implicitly normalizes using Clausius-Clapeyron. And that's mostly between 0 and 1. And these distributions don't necessarily need to be aligned for the neural networks to do well. But if you have a feature and its support is significantly out of distribution, then you don't expect the machine learning algorithm to work well. And if you just do this rescaling from specific humidity to relative humidity, and sorry, I need to hide the bar, you already do much better. And so that's an easy game to play with specific humidity. And you can also play this game with all of the other features. So we we transform temperature into a version of coarse buoyancy that was developed by UCLA. That was a collaboration with David Nealing's group. You can transform surface enthalpy fluxes until the distributions don't necessarily perfectly align, but at least have a shared support that the neural networks can deal with. And then you're approximating what we would call a climate invariant mapping. And what we did, if we take a step back, is we use a physical knowledge to transform the data so that the mapping that was learned by the neural networks was generalizable by design. And I want to insist this is approximate knowledge. This Pune buoyancy metric is by no means the ultimate answer of the best temperature transformation you can ever come up with, but it's physically grounded. It's a more static energy conserving plume buoyancy metric that you can form at the coarse climate scale. It's a physically grounded metric that allowed us to recast what the machine learning algorithm was learning in a way that generalizes across climate. And we tested it on 3 different climate models. I'm showing you the results also in a realistic geographic configuration. I'm showing you maps of coefficient of determination, not to be confused with the Pearson correlation coefficient. So 1 is 1 minus MSE divided by variance. So 1 is perfect prediction. 0 means the error is order 1 standard deviation, and then it can go all the way down to minus infinity for an infinitely bad prediction. And you can see that before the transformation, if you look at the predicted mid-tropospheric subgrid heating, we had this whole generalization gap, especially in the deep tropics that are particularly moist. But with the transformation, we don't do perfectly, but we're already doing much better. And that's even truer if you look at variables that are a bit more atmospheric centric. And so I hope I convinced you that in the case, by just transforming, like slightly shifting what you were learning, we built, without seeing any data from the future, a mapping that was generalizable thanks to physical knowledge. So to me, that's a clear example where even in a high-dimensional case, physical knowledge helps you better generalize, even in cases where you don't have perfectly exact knowledge that you can write an equation from. And now you can ask yourself, why? Why did this work? And so what we did is we use a game theory-based explainable AI library called CHAP. It has nice properties. That's why I like to use it. Like all post-hoc XAI, it can be criticized. I'm happy to go to talk more about it in the discussion during the Q&A session, sorry. And what we can do is we can create nonlinear response matrix to understand the kind of mapping that the neural network learned. So these matrices tell you how each vertical level of your output responds to each vertical level of your input. This is surface, this is space, this is surface, this is the surface, this is, wow, sorry, 2-hour lecture. I should be a bit more focused on this. This is the surface, and this is the tropopause, the average tropopause level, and this is space. This is the surface, this is the average tropopause, and this is space. You can plot this nonlinear response matrix for the climate invariant mapping on the left, or for the mapping built directly from the raw data on the right. And what is the difference? And at first, what you see is just as a bunch of red and blue on the right, while it's nicely following the diagonal on the left. And what that means is that the neural network learned a mapping that is more what we would call vertically local. So when framed in temperature-specific humidity coordinates, you need knowledge of these variables at different levels to just understand how convection responds, because you need the full boundary layer conditions, you need the right combination of temperature and specific humidity to form a cloud. But when you transform the data, it's much easier because relative humidity directly more or less tells you when the clouds form. And this measure of buoyancy tells you which, when the boundary layer, to put it in really, really simple terms, it tells you how the boundary layer talks with the troposphere. More specifically, by just giving you that, it's a non-local metric, so by just giving you a value at one level, it gives you the proper stability conditions in the atmosphere that allow you to understand when convection is triggered or not. And so in this case, we uncovered an invariant transformation that simplifies the mapping a lot. So imagine you were trying to write an equation. On the right-hand side, it would be a messy integral differential equation, where on the right-hand side, it's a local response, so you have a shot at writing it as a partial differential equation in the vertical. And that's a good transition to the data-driven discovery part of my talk, how you can use machine learning and data to learn potentially new physical knowledge. And I have a whole outline, but before I go, I want to give everyone a chance to ask questions, and you can decide whether you want to ask question now or whether you want me to go a bit further until 12:30. I'm happy to adapt to whatever would be most logical for the STEM school.
Yeah, I think Tom, you can carry on now, and maybe after after this part, then we can have all the questions together.
Do you want me to give maybe go one section further and then we'll take questions?
Yes.
Because I'm looking at the time, and if you want a strict stop at 12:30, I think I can go one section further.
Yes, yes.
Okay, perfect. Okay, so I'll give you an overview of an article we just published. It's my latest first author paper. It was linked in the reading. And the idea is, if we have machine learning algorithms that work well, we've probably learned something. How can we frame what we learned in a way that humans can understand? And therefore, in a form of knowledge that we can then use for new scientific discovery. So I'll be advertising what I call Pareto optimal model hierarchy. And it's motivated by the fact that the added value of machine learning is measurable through performance metrics, through error metrics. This is an example review from Stephen Rasp and Stephen Hoyer from Google, where they track the scale of data-driven weather model as a function of the date that they were released. And what you can see is that 100 is a bar of state-of-the-art physically based dynamical forecasts, more specifically the HRES model from ECMWF. Pengu was the first model that just went over that bar, and then GraphCast and the neural GCM kept improving on it. So clearly we can measure, we can say machine learning learned something, right? Because we were able to crush the best weather model. But then if you ask why, it becomes a lot harder. This shares a bit this increase, and the reason why it's so hard to explain is these models became more and more complex. And this shares a bit of analogies with how Earth system models were developed over the years. So that's a nice schematic from a review led by Simona Bordoni. And she really nicely illustrates how as we added more and more processes to our Earth system models, they become larger and larger beasts that we can't possibly understand. Once you had snow, sea ice, aerosol, the carbon cycle, etc. And so the climate community was faced with this challenge for quite some time, because climate science, or at least Earth system models, serve the dual purpose of not just predicting, but also understanding. So we've always wanted to understand. So the community has developed what we call climate model hierarchies. And they're becoming trendy again. I'm seeing more and more reviews on climate model hierarchies. This is great. That's an older one. A one from 12 years ago from Sandrine Bonny, where she plots system complexity, model simplicity versus system complexity, and argues that by having the right types of models in experiment, you can go between realism and understanding. And inspired by this, I'm going to pitch what I call pseudo-optimal model hierarchies. So imagine you have a lot of machine learning models. Some of them work very well. How do you distill knowledge from that? The base idea is simple. You should just work in a really well-defined error complexity plane. It can be as simple as a two-dimensional plane where on the x-axis, I keep track of model complexity. I'm not going to tell you what the best complexity metric is because I don't know. It's an entire field of research. What I can tell you is that if you want to compare all your models, you should probably pick a complexity metric that you can calculate across all of your models. And so I'm just going to take number of trainable parameters because that I can calculate for simple physical, semi-empirical machine learning models. And on the y-axis, I'm going to keep track of model error. Again, there's no perfect error metric. I'll show you MSE here, mean squared error, because it's a regression problem, but you can generalize whatever I'm saying to n dimensions. Just whenever I show you a line, just imagine it's a hyperplane. So, you can add as many error metrics as you think is important. And now imagine you trained a bunch of data-driven models. So you have a lot of different data-driven models and they're all scattered here. And you're trying to ask yourself, okay, within all of these models that I train, which one is the best? And if I'm seeking knowledge, usually what I want is the simplest possible model that performs well. So what I'm trying to go for is the bottom left corner of this plot. And I'm going to give you 5 seconds, within all of these models, which one is the best? So I'll let you think about it for 5 seconds. And then you probably know by now that there's not a single answer. Because we have more than one performance metric, it's a set of models that's optimal. And we can define what we call the Pareto front, which is a set of models where you cannot switch out of these models without compromising at least one of these two metrics. So it's a multi-objective optimization concept. So for example, this one looks optimal. And if I switch to go to this one, I'll lose in error. If I switch to go to this one, I'll lose in simplicity. So it can be defined using set notations. In practice, all you do is you draw a staircase from the top left to the bottom right. And these are Pareto optimal models. What machine learning models are really good at is learning high-performance models that are very complex. I think we had that, we already had that discussion during one of the questions. There were a lot of really good questions today, so it's good. That the reason why we don't, if you just throw symbolic regression at a problem, you get equations that don't quite make sense, is because these equations are stuck in the top part of the plot. They're not really optimal in any way. What usually is easy, at least as a first step, is to train neural networks, a really complex model that can describe the data well. So what we get is really complex model that result in a step improvement in error. And then you can ask, why? Why are they better? And in that paper, what I argue, along with my co-authors, is that it can be understood if you explicitly write the equation. It can be decomposed into roughly 4 categories. So you can just write, the output of my model is the function learned by my model of, in a geoscientific context, physical fields that have been discretized in space and in time. And if I improved y, I must have improved something on the right-hand side, right? There's no magic here. Could be m. Maybe my machine learning model learned a better function. So I had a simple linear model and I crushed it because my model learned that the data is actually closer to an exponential. Maybe I learned a stochastic mapping. I learned to better describe the spread of my data points. There can be an improvement in x. So what's interesting and what often happens is that machine learning algorithms can use physical fields you may have never been able to use before. Often simple models struggle when there's two really closely correlated fields, but very expressive machine learning algorithms, as long as these fields contain different information, can use all of these different fields. So maybe you're now able to use a field that you weren't able to use in your models before, and that leads to a better model. Maybe you're better able to use information in space. So, for example, deep learning architectures in computer vision come to mind immediately, right? Convolutional neural networks, transformers can better learn teleconnection, different relationship in space. Same in time, sequence processing algorithms, so recurrent neural networks, also transformers if you put the attention layer in the right direction, etc. Maybe you're able to better learn, for example, to exploit the past. And I think this gives a nice categorization of the kind of value of knowledge that you can, quote unquote, distill from your machine learning, from your successful machine learning algorithm. Functional representation, feature assimilation, spatial and temporal connectivity. And so then the distillation step is to bring that added value back to a simple space, or to be a bit more quantitative, to a model that has a lower complexity without sacrificing performance. And that's what I call distillation. And I'll give you the example of symbolic distillation, which is equation discovery, in a second. So I'll do it on cloud cover parameterization. And our motivation here is similar to the ones I gave you for the hybrid AI climate models, is that I want to use storm resolving data, all these high fidelity simulation data, to improve my existing cloud cover parameterization. So what we do is we're going to take the original cloud cover from a storm resolving model. And so for that, you just take the high resolution data, you apply a threshold, so it can be a threshold in cloud condensate. And you can say, okay, if I'm above this threshold, there's a cloud 1. If I'm below this threshold, I don't have a cloud 0. So you have a maps of 0, 1. Then I'm going to bring it to the scale of my coarse climate models. And then the goal is just going to be to map the left to the right. So that's a very straightforward machine learning task. It's straightforward, but it's not easy. I want to make that point with a movie from the North American monsoon. You can see that, for example, if I look at cloud cover, this is the area or the volume fraction in this voxel. So this is a beautiful movie. I spoiled it by drawing a voxel. That's what you have in your atmospheric models. And so you can see that there's very different conditions that lead to the same cloud. Sorry, we have blinds automatically shutting down. My picture is going to work again in 2 seconds. Very different conditions can lead to the same cloud cover. It's a non-trivial problem. And then clouds, depending on how they spread, can lead to the same cloud area fraction, although they can be ice or liquid clouds with different properties. And we'll come back to that later. And so now I'm showing you a concrete example of what these period-optimal model hierarchy look like. This little star here is the parameterization that's currently in ICON, the one we wanted to beat. It's a Sungvist parameterization. And here we trained linear polynomial models. This is a much better parameterization. It's a Wong parameterization that with just 4 features, it allowed to do quite well. These are my baseline models. And then in Grudner et al. 2022, so this is a work led by Arthur Grudner, who is a PhD student in Veronica Ehring's group I work closely with. He showed that you can train a neural network to properly emulate storm resolving cloud cover. Then you get that performance improvement I told you about. But these neural networks have 10,000 or 100,000 parameters. They're hard to interpret. You can use post hoc explainable artificial intelligence, but they don't give you the full picture. But what you can do is you can use these neural networks as a guide to better understand what you learn that wasn't available before in the previous baselines. And in that case, we mostly use it for the 2 first aspects I told you. Functional representation, we looked at the nonlinearities that the neural network had learned. And feature assimilation. We use neural network for nonlinear feature selection. So out of the hundreds of variables in combination we could use, we keep the neural networks that work the best, and that way we can identify the top features that can be non-linearly processed to yield optimal cloud cover. And then we feed that in a symbolic regression algorithm. There's a lot of them. They're benchmarked, especially in the biomedical field. They have really nice symbolic regression benchmarks. Here I'm using PySR, whose lead developer is Miles Cranmer, who's a professor at Cambridge. He's just an incredible scientist. And that library works really well, and it's very easy to use. It's based on evolutionary algorithms. But the problem is these algorithms don't scale very well, so you can't, neural networks can deal with a lot of features, but these usually, you don't really get good results above 5, 6 features. But the neural networks told us which features to use, so we can just pick these features and feed them to this algorithm, and then we get a family of equations. I talked to you about physics-guided machine learning, so we use a set of 10 constraints to reduce that set to a plausible set. And then in that set, the best Pareto-optimal equation has 3 terms that are physical. There's one term that's just a Taylor expansion about the mean state. It's just a standard thermodynamic term. It makes cloud cover react to relative humidity and temperature in a way that you expect. To first order, for example, a more humid atmosphere will have more clouds. A warmer atmosphere will have less clouds. Nothing new. What's new, though, is the feature assimilation part. The neural networks were able to detect that the vertical gradient in relative humidity was the best feature to place the stratocumulus depth at the right place on Earth. And these are particularly important because they're the source of some of the main biases we saw in CMIP5 and arguably in CMIP6 a bit as well, where the amount of radiation reflected by clouds, especially by low clouds, was very uncertain and was leading to large uncertainty. So placing these clouds at the right place, thanks to just this one feature that we process here using a polynomial of order 3 with interpretable front coefficients, is able to place the stratocumulus depth at the right place. And then we have this last term where, and that's going to be my message for knowledge discovery, so I want to insist a bit on it, where we were surprised. And I think that's going to be my main message, is if you want to learn something new from data and machine learning, you have to leave room for surprises. If you constrain the entire framework and you leave no room for surprises, you're not going to learn anything new. It's trivial, but there's so many papers that don't leave room for surprises or leave too much room for surprises where you go to completely unphysical solution. But finding that interesting middle where there's room for knowledge discovery is really important. And here, I'll give you an example. It's not purely new discovery, but it felt like it, at least when we saw it, before we read some papers from the 80s. There's always a paper from the 80s or the 70s that already did what you did in some way. But we confirmed that the optimal cloud cover parameterization doesn't handle the liquid and the ice clouds the same way. So what was really interesting is that in our learn coefficient, the coefficient in front of the liquid and the coefficient in front of the ice were of different magnitude. And you can ask why. When I counted the 0 and 1, I didn't treat liquid different than I treated ice. But what happened is that the subgrid distributions are different, and it's working off the voxel average. And so it's implicitly learning the subgrid distribution through that coefficient. And for example, because there's less high-resolution pixels with ice, it learns that if there's a lot of ice, it's probably spread out more, so it should lead to a larger cloud cover. And so it's putting a higher front coefficient in front of the ice term. And so to summarize, what we did here is we were able to, starting from baseline models and using neural networks as just the first step. It wasn't our ultimate step here. We didn't stop at the neural networks. A lot of papers are stopping at neural networks for discovery when they could go so much further. We identified the nonlinearities and the features we were missing. and brought it back to equations that crush all the baseline. They don't do as well as the top neural networks, but they do a lot better than the baseline, than the equivalent to a neural network, that have 10 or 9 parameters. And then at that stage, you won, because the equation is so simple that you can just read it and understand what you learned that you didn't know before. An example of transparent machine learning, and now that parameterization only has 9 or 10 parameters, it's a lot easier to calibrate inside a neural network model. And because it puts the clouds at the right place, it reduces the biases in cloud cover and in the top of the atmosphere with respect to observations. So on the right is the model with the traditional parameterization. On the left is with the cloud cover parameterization. These are fresh results from a preprint that's on arXiv. And here we were able to improve the biases in the top of the atmosphere along with vegetative budgets. And that's really important because, for example, in climate modeling, that's one of the main things we're trying to do better, having better top of the atmosphere and surface vegetative fluxes. And so to summarize, can we learn anything new using ML, or I often get the question, have you learned anything new using machine learning? I can't really say yes or no, because when you make a new hypothesis, it has to be tested in many different ways, but at least we know that we can. We can go further than just merely confirming existing hypothesis. And as long as we keep track of a model, and so that's really why I insisted on this hierarchy, where you can cleanly see by following this Pareto front what the value of each added complexity is, you can make new hypotheses based on the improved performance of machine learning in a clean way that you can't really do with XAI, where you fit a model on top of a model. And so with that, I think I'm going to stop this part to stay on time. Thank you all for your attention, and maybe I'll take questions about everything I've covered. I can also send you the slides with the entire talk if you're interested. And you have the article references, I think, in the ICTS schedule.
Yeah, thanks a lot, Tom. That was a really wonderful and informative tutorials, and I think students also enjoyed it. So, any further questions from the physical audience?
Again, I have question.
Yes, please.
So, can you please explain again what the transformation you have applied for that climate invariant machine learning?
Yes, but the best is just to go to the paper where all the equations are in the appendix if you really want to know what I did. But I'm going to tell you qualitatively at a high level what I did, and then you can go in the paper if you're interested.
Yeah,
so here what we do is we make hypotheses about possible transformation. So for each feature, we say, okay, specific humidity, what is the literature telling us about how we may transform it to make it more invariant? So for example, you can do saturation deficit or relative humidity. And then you can test, right? You can test, okay, between these two transformations, which one works best? You can repeat the same game from temperature. So for temperature, you have several different transformations you can make. And in that case, one we picked, and it's because we knew most of our subgrid scale fluxes are linked to radiation. We used work that was linked to the Go Amazon Field campaign, where they found a measure of buoyancy that can be framed at the core scale, and that described the evolution of not just individual convective systems, but also mesoscale convective systems. And this is so the tricky thing is to really calculate the buoyancy field, you need really high resolution data, right? Because you want to calculate density anomalies. So to define it at the core scale, what you do is you say, okay, I'm going to raise a parcel and define buoyancy that way. So you have to make some conservation assumption. So we raise a parcel from the surface, conserve more static energy, and that gives you a measure of that buoyancy. And that's the variable we use to transform temperature. For surface enthalpy fluxes, we use the bulk aerodynamic formula to normalize out the saturation deficit that is not climate invariant. Does that make sense? Or?
Yes. Thank you.
And all the equations are in the paper in the appendix.
Yeah, I think you can, Tom, it will be really helpful if you share the slides. So you can share it with me and I will forward it to the entire audience.
Yeah,
And
and the papers I think I already shared with you all.
Yeah.
I think
yes, it's already shared. Any other questions? Yes.
Hello, sir. Sir, it's Shreyashi. Sir, I wanted to ask that if you, what different would you do if you were to do the same thing that you did with GCM over a regional weather forecasting model?
I'm not sure. I'm not sure if we get the question because I did many things with GCMs. So
Like I meant to say that you incorporated a machine learning algorithm to in place of parameterization. So if you were to
right.
do the same thing of regional weather forecasting model, so what different would you do in that?
I don't think it's so different if you want to do the same. If you want, I don't know. Imagine you running WRF and you want to improve your WRF parameterization, or any kind of regional forecasting model. All you would do is you would need to collect high fidelity data and train a parameterization for that regional model. I actually think it's easier. I think it's a more tractable problem. I mean, especially if you have data mostly over a region, it's a lighter, slightly more tractable problem. I think it may be a bit easier actually to do for a regional model. And it has been done, right? If you go on that page that I linked, there are examples of hybrid WRF that you can use, and there's a lot of literature on what you just said. So what you suggest is a good idea. It's been done, and I don't think it's fundamentally different. Maybe the one caveat is that, especially if you're going to use neural network, it works best when you have a lot of data and that data is very varied. So all the generalization problem I talked about, you can get rid of a lot of them by just having data from all the different climates, very extreme cases, throwing it all together, and then you get a very generalizable training set. And so that may be a challenge with the regional model. If you only collected data in a small region, you may not be able to train the parameterization the way you want. So maybe if you're doing it, if you want it to be very robust, you should run your regional model in completely different regimes and completely different regions and collect data that way. If that's your setup, right? If you're not directly training it from observations.
Thank you, sir.
Yep.
Okay, anyone else? Okay, there's an online question. How distillation using symbolic regression from neural networks is done? Do we optimize over some intermediate features or output of the neural network?
Okay, so in the case I showed, I did it very naively, and you can read the paper for that. I'm more thinking in terms of what we learned from the neural network, and in that case, it was mostly feature selection. So we use neural network for nonlinear feature selection, and once we have the features, we just use these features to train the symbolic regression. So we don't do the symbolic regression and the distillation as part of the neural network architecture, but it's done. So I think if you look at PDNet or DNet, there's these nice architectures where you have symbolic layers. There's also the Kolmogorov-Arnold network that just came out. I don't know how well they really work for that purpose, but they replaced, they have learned activation function. They replace what you learn, they put it in the activation function rather than at the node place. And you could technically sparsify one of these networks and learn an equation that way. So there are methods out there where you can learn the equation directly on the neural network. But in our case, I tend to have two steps. One way I train the neural networks to get the maximal possible performance for a given data set, and then understand what I gained, and then use this knowledge of what I gained, like run many different experiments, so cross-validation experiments, to then distill that into an equation in the case of symbolic distillation. But you can think of different types of distillation, right? You could also distill it in a simple schematic. You can, in the paper, we have examples where we distill it in terms of how much memory you can recover given for a given spatial granularity. So you can distill knowledge about the spatiotemporal characteristics of your system. In all cases, I would refer you to the distillation paper to know how we did it, knowing that there's a lot of papers out there where you can also learn the equation as part of the neural network. But I'm not sure it would work as well because then the optimization is compromised a bit.
Okay. In the offline audience, there's a question.
Yes,
Nishant, you have a
yes,
question?
Nishant again. Actually, I wanted to ask if does this PINN solve that interpolation and extrapolation problem that we had in PGML?
No, at least not in my opinion. Like Pin doesn't solve it, and in the climate invariant neural network paper, at least there's one intermediate version where I physically constrain the neural network, and that's not enough to make it generalizable. So there's a part of the literature that's very misleading in applied math and physics that works on really low dimensional systems where everything works, where you constrain it and then tell it generalizes better. I would argue that's not true, and you can mathematically prove that's not true for higher dimensional systems, where it's not because you reduce the degrees of freedom a bit that your model is going to generalize to any regime it's never seen before. So I would say in general, it may help to physically constrain it or to have a physically informed architecture, but it's not enough.
Okay.
And then you had a second question?
So done. Thank you so much.
Bye.
Okay, then thanks a lot, Tom, for an extremely like very clear and very interactive talk. I think the students also really enjoyed it, and we had lots of questions. It was very insightful for everyone. So let's put our hands together for Tom.
Yeah, and thank you so much for inviting me. I really wish I could have come, but it's very far, and I have my own group to take care of here, so it was hard to travel.
Okay, yeah, we understand. Thanks a lot, Tom, and hope to interact with you more again in future.
Yeah, thank you so much. Have a good one.
Okay. Bye, Tom.